So our study is about the projectile motion of a thrown baseball. The purpose is to compare the time and distance of flight in a real-life trial to the expected time and distance of flight if air resistance is negligible. The materials were 3 tripods, a pocket radar gun, 3 iPhones, scale, baseball, and Google Maps. For our methods, one member held a radar gun horizontal to the thrower to get the horizontal velocity of the throw, and we placed 3 tripods in the field, one behind and one to the right of the thrower, and the last one was at the opposite zone. So the data that we collected was the initial horizontal velocity, which is measured at 80 miles per hour, the time of flight, which is 4.6 seconds, and how far the ball flew, which is 308 feet. This is the subject completing the trial.
The first thing we had to find was theta. In order to find theta, we overlaid 2 images taken in the video, and we calculated the distance between the two points of the baseball in each image. So you can see both positions there. We measured the positions by counting the pixels at each position. So in position 1, the x component was 680.8 pixels, and the y component, y1, was 153.3 pixels. We then calculated the position for position 2. So the x component for position 2, x2, was 819.8 pixels, and the y component was 70.0 pixels. After we found those, we then calculated delta x and delta y. Delta x was calculated by taking x2 minus x1, so 819.8 minus 680.8, and that equaled 139.0 pixels. We then calculated delta y by taking y1 minus y2, so 153.3 pixels minus 70.0 pixels. That equaled 83.3. And then in order to find theta, we did the arctan of 83.3 over 139.0. So theta equals arctangent of 83.3 over 139.0. And that equaled theta equals 31 degrees. And the next step was setting up the system. So h is the height at which the ball is released, and theta is obviously the angle at which the ball is released. X initial is equal to the goal line, so that's the start, so it's 0 yards and 0 meters. And then X final, as shown there, was measured to be 308 feet. Which is equal to 94 meters. The next step was finding the initial velocity and the initial vertical velocity, and what I just bracketed is all of the information we've already calculated and collected. So the initial velocity is the hypotenuse, and the initial vertical velocity is v naught. The initial horizontal velocity was measured at 35.8 meters per second by the radar gun. So the first step is calculating the initial velocity, so v naught. V naught is equal to cosine theta, which is equal to the initial horizontal velocity over the initial velocity. Theta, as already found before, was 31 degrees. So cosine of 31 degrees is equal to the initial horizontal velocity, which is 35.8 meters per second, over the initial velocity. So the initial velocity is equal to 35.8 meters per second over the cosine of 31 degrees. So that is equal to 35.8 meters per second over 0.86. So the initial velocity is 41.8 meters per second, which is equal to 93.5 miles per hour.
Next thing we had to calculate was the initial vertical velocity. In order to count the initial vertical velocity, all we did was sine of 31 degrees, or sine of theta, equals the initial vertical velocity over the initial velocity. So v naught over v naught. So sine of 31 times initial velocity equals the initial vertical velocity. So the initial vertical velocity is equal to sine of 31 times 46.8 meters per second. 41.8 meters per second. So the initial vertical velocity is 21.5 meters per second. A brief correction to the last video. V naught is not equal to cosine theta. That's just how you solve for V naught. It's the same on the other side, where V naught is not equal to sine of 31. That's just how you solve for V naught. The next thing we had to calculate was expected time of flight, and we used the last kinematic equation on the screen to do that. So x equals x naught plus v naught t plus 1/2 at squared. In this situation, it was the final vertical position equals the initial vertical position plus the initial vertical velocity times time plus 1/2 at squared. The final vertical position was 0. So 0 equals, and the initial vertical position equals h. So h plus the initial vertical velocity times time plus 1/2, and gravity is the acceleration of this, times t squared. So 0 equals 1.96 meters plus 21.5 meters per second. T plus 1/2 times negative 9.8 meters per second squared times t squared. So 0 equals 1.96 meters plus 21.5 meters per second times time plus or minus 4.9 meters per second squared times t squared. In order to solve for expected time of flight, we use the quadratic equation as shown there. So t is equal to the quadratic equation. So once you plug in all of the information from above, you get this equation. And to speed up the process, we're just going to show you the steps that go to make it simplified and just the simplified form. This is the work needed to simplify the quadratic equation. And you can see there the arrows point to the next steps. So once you get it simplified, you have two possible answers, and it's when you do the plus or the minus. So the first one is not possible because you can't have a negative time. So the expected time of flight was 4.5 seconds, and that is without air resistance. Lastly, we calculated the expected distance if air resistance was negligible. So the expected distance was the initial horizontal velocity times the time t. So the expected distance was 35.8 meters per second times the calculated time, which was 4.5 seconds, which is equal to 161 meters, which is equal to 528.2 feet. So the expected distance that the ball would travel was 528.2 feet. This is our data. The calculated time of flight was 4.5 seconds and the calculated distance was 161 meters. The collected data, the time of flight was 4.6 seconds and the collected distance traveled was 96 meters.
The purpose of this experiment was to compare the expected versus calculated distances and times of flight for the projectile motion of a thrown baseball. We found that the expected and calculated distances were significantly different because air resistance was not factored in for the calculated distance. Therefore, air resistance plays a major role in the distance the ball travels. For time of flight, the expected throw was the same as the calculated throw, thus indicating that air resistance did not have an effect on the time of flight. In conclusion, we were able to use kinematic equations to compare how air resistance affected the expected and calculated distances and times of flight during the projectile motion of a thrown baseball. We found that air resistance had a significant effect on the expected distance the ball traveled when compared to the calculated distance that neglected air resistance.